Hello there. In the last lecture, we looked at practical free vibration analysis, and now we are done with free vibration analysis. Now, what we are going to do is that you are going to be looking at a lab situation, and in the lab you will find you'll be taken through how to do a multi-degree of freedom system and to find out its frequencies and mode shapes. Okay. So, I am going to stop here as far as free vibration is concerned, and I am going to move on to the dynamic analysis of multi-degree of freedom system problems. So, now the final one as far as multi-degree of freedom system problems is dynamic response of we are going to be looking at multi-degree of freedom dynamic response. Okay. Now, dynamic response, well, let us start. Remember last time I did say that you could remember I said we spent a little bit of time on damping matrix, but just right now let us not worry about damping. Let us look at the undamped system response. Okay. So, undamped system response is essentially this, subject to initial conditions given by these two. Okay. So, this is the problem that we are looking at, undamped system. So, we have m v double dot plus k v is equal to p, where p is the load vector, m is a mass matrix, k is the stiffness matrix corresponding to the degrees of freedom vector given by v, okay, and subjected to initial conditions v 0 and v dot 0. Note that all of these are perforce vectors because it is an n degree of freedom structure. Okay. So, now how do we solve this problem? Well, let us start from the beginning. Again, I just showed you in the last lecture that, well, we can indeed write the displacement as a sum of I going from 1 to n phi I yi. Okay? And so, if you look at this one then in essence becomes the following, that phi 1 y 1 plus phi 2 y 2 blah 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 plus phi n y n, and I can write this in matrix form in this format. This is an n by 1, this is an n by 1, this is an n by n. What is this vector? This vector is vector of the modal amplitudes. What is this? This is a matrix whose row vectors are, so each row of this vector is this. Okay. Anyway, so now we also saw that, look, so that means if I know the modal amplitudes, if I know the modal amplitudes. If I know this, I can find this because this is known from free vibration. Okay. So, the way of going from y to v is relatively easy. Okay. Now, how do I find out y given v? Well, we have also done that. We did that and we saw that using the orthogonality condition, right, y n, I am just repeating something that I have already derived, it's equal to phi n transpose m v upon phi n transpose m phi n. Okay. So, using the orthogonality condition, I can always find this out, and so from given v to find out y, okay, this is the way of finding it out. Given v, finding out y n, and then you have got y. So, v to y is through this, and y to v is through simple. V to y this, y to v this. Okay. So, now given this, I can write my equation of motion. Let us look at this equation. This is m v double dot plus k v is equal to p. Okay. So, this is how this is written. Okay. Now, let me write. I know I want to write down v in terms of y. What will it be? It will be m into, now this is phi into y plus k into phi into y is equal to p. All I have done is substitute the fact that v is equal to phi y, and obviously v double dot, phi is not a function of t. So, the only thing that is a function of t is y, and so that is what comes, right, and that is all I have done. Okay. Now you know what I am going to do? I am going to as long as I pre-multiply all terms on the left hand side and right hand side by anything, it should be valid. Okay. Now that what I am going to pre-multiply, now note here that this is n by n, n by n, this is n by 1, this is n by n, n by n, n by 1, and this is n by 1. So, this is actually a set of n differential equations coupled, because even if m is lumped mass, k is still coupled. Okay. So, we have a problem. Okay. So, now let us see, I am going to pre-multiply this entire thing by phi transpose, which is an n by n, where what is phi transpose matrix equal to? Now, this matrix is equal to, its row vectors are equal to phi 1 transpose phi n transpose. This is what this n by n matrix is. So, phi n transpose is that into m into phi. This is an n by n, this is an n by n, okay, and plus phi transpose k phi sorry, this is y double dot, this is y is equal to p. Again, all of these are n by n. Okay. So, this matrix and oh, by the way, sorry, phi transpose. Now, this is an n by n multiplied by n by 1, it is still an n by 1. So, what we have is we have continued taking a n coupled linear differential equations, transformed it into still n coupled differential equations, and then this is also n differential equations. But let us see something very interesting, and that is, let us see what this phi transpose m phi. Now, this is an n by n, which is nothing but phi 1 transpose, phi 2 transpose, blah blah blah, up to phi n transpose into m into what is this? This is phi 1, phi 2, blah 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 till phi n. So, every row here is a mode shape vector, and every column every column over here is a mode shape vector, and every row over here is a transpose of the mode shape vector. Okay. So, now let us do this. So, this is a 1 by n, this is a 1 by n, all these are 1 by n, and so 1 by n's, n such give you n by n. This is an n by n, and these are n by 1, n by 1, each one is a row of n by 1 vectors to make an n by n. So, let us see this entire thing, what does it look like? What does this matrix look like? Well, I can easily see this is a row is multiplied with a column. So, that one, if you look at it, so the first one, if you look at it, what does it represent? It represents 1 by n, let me see what this represents. This is a 1 by n, this is a n by n, this is a n by 1. What is that? N into n by 1 is n by 1, 1 by n into n is a scalar. So, this is in this matrix, the first one is this. What is the second one? Phi 1 transpose m. Now, let us see. Phi 1 transpose m phi 2. What is that? I mean, and all of these, it goes up to phi 1 transpose m phi n. What are these? By definition, this is m 1 and these are all 0, orthogonality property. Okay. So, if you look at this matrix, the next one is phi 2 transpose m phi 1, phi 2 transpose m phi 2. So, if you look at this one, this matrix looks like this: m 1, m 2, zero, 0. It is just a diagonal. This is a diagonal matrix. Okay. Let us now look at phi transpose k phi. Well, let us see what phi transpose k phi turns out to be equal to. It is equal to, same thing, phi 1 transpose, phi 2 transpose, phi n transpose into k into phi 1, phi 2, phi n, okay, and then is equal to, what does it become? It becomes nothing but phi 1 transpose k phi 1, okay, and all other terms are 0. Again, only the diagonal terms exist because all the off diagonal terms are 0 because of what? Because of orthogonality property. Note that since these are all 1 by n's and these are n by 1's, this each one, even though it is a matrix multiplication, is actually a scalar. Okay? So, therefore, a very, very interesting thing. What happens now? Once I have put this, once I have put m phi transpose into y double dot plus phi transpose k phi into y is equal to phi transpose into p. Okay. What is this? A diagonal matrix. What is this? A diagonal matrix. So, what do we get? If you look at this, now we just get note that by this procedure, okay, I have transformed a problem which was in the original space. In the original space was n coupled linear differential equations. I have, by transforming it into the normal space, the modal space is called the normal space. The modal space is also called the normal space. By transforming it from the original space to the modal space, what have we done? We have taken n coupled linear differential equations and made them into n uncoupled linear ODEs. So, therefore, you look at this, this does not have any other y. It does not have any other y. Okay. So, if I look at this problem, and now let us look at something else. Let me just look at something else, and that is, what is phi n transpose k phi n? Let us look at it. Phi n transpose k phi n. What is k phi n equal to? K phi n is equal to omega n squared m phi n. Now, omega n squared goes outside, omega n squared is outside because it is a scalar, and so what you have is phi n transpose m, which is omega n squared m n. So, if you look at this problem is this, if you look at it, because you look at this, what was m into v plus k into v is equal to p, okay, and what is k? K is equal to omega squared m, because k upon m is equal to omega squared. So, so I could substitute in this way. If you look at this, this is identical. This is identical to a single degree of freedom system. So, what we have done through this procedure, by incorporating the fact that V is equal to, we have taken it from original space to normal space, because these are the amplitudes in the normal space. These are the amplitudes in the this thing. Okay. By doing this, I have taken coupled equations, taken them n coupled ODEs to which is equal to omega n squared mn, yn is equal to Pn. N uncoupled single degree of freedom ODEs. Okay? Brilliant. So, you've made a multi-degree of freedom problem into n degree of freedom, multi-degree of freedom problem into n single degree of freedoms. So, you've taken the entire problem and made it into a single degree of freedom problem. Okay. Of course, note that this one, how do I evaluate these? Well, Mn is equal to phi n transpose m phi n. So, you still have to do these, and Pn is equal to phi n transpose the load vector. You still have to do these, and omega n squared comes from the free vibration analysis. So, once you do these, you get this, you got n uncoupled differential equations, much easier to solve than n coupled differential equations. And once you solve for these, now these will be solved for what? Right? This is the general kind of problem, single degree of freedom problem. Well, how do I find out y n 0? Very, very simple. Why can't I find out y n 0? I have already done it. Y n 0 is equal to phi n transpose m v 0, which is v at time t equal to 0, upon phi n transpose m phi n, and therefore, y n dot is phi n into m n. Note that none of these other terms are dependent on time excepting for these two. So, automatically this comes in. I can find out the initial conditions through this procedure, okay, using the same thing. Okay. Remember that in one you go from V to Y, this is the going from V to Y, and the other one is going from Y to V. So, once you have solved for these y n, okay, you plug it back in here and you have got your displacement time history. Okay. So, this is a fairly easy way of doing things. Okay. And this approach of solving these problems is known as the mode superposition method. And as all superposition methods, this is only valid when you have a linear system. Okay. So, this, what is the mode superposition method? The mode superposition method is based on the fact that any displacement quantity time is given by phi I going from 1 to n. This is your mode superposition, where phi I is a mode shape which is time independent, and the modal amplitude is time dependent. So, based on this and using the procedure, so once this is the basic mode superposition, that is what we are saying. Okay? And once we have this, and so the problem then becomes this. Okay? Let me write it down in an algorithmic fashion as to how you are going to use the mode superposition method to solve a multi-degree of freedom problem. Start. 1. Define degrees of freedom. Define the degrees of freedom. That will give you this, right? So, once you do that, then corresponding to this, find M, K and P vectors. Okay? So, mass, stiffness and find that. Then solve this free vibration eigenvalue problem for omega n and phi n. 4. Find all phi n transpose m phi n, that is mn, phi n transpose p, which is pn, and then solve n single degree of freedom system problems, where m1 omega 1 dot plus omega 1 squared m1 y1 is equal to p1 of t. Well, this is a single degree of freedom. We already have solved many single degree of freedom problems. Okay, given so find this and also find out y n and y n 0 from v 0 and v dot 0. So, that basically you can solve this differential equation given initial conditions. Okay. So, once you have done that, so now this one gives you what? You solve for it and you get what? Think back to the single degree of freedom. Single degree of freedom gives you y n of t. Find y n of t using single degree of freedom response analysis procedures. So, find y n of t. Once you find y n of t, v of t is equal to summation I going from 1 to n phi n, sorry, this is phi n. So, phi n y n of t, that gives you your displacement. In fact, we can show later on, we will see that you can find out any displacement, any response quantity can be found out in terms of these modal amplitudes. And response analysis, because this is nothing but response analysis of multi-degree of freedom system problem. So, we have solved the undamped problem completely. Okay? So, we have solved the undamped problem. Now, let us look at the damped problem. And today, I shall only introduce you to the concept of the damping. And remember, I talked about proportional damping. Well, we will see. If you look at this, see, we are getting, by using mode superposition, we are getting the equation which looks like mn yn double dot plus omega n squared mn yn is equal to Pn. This is a single degree of freedom. It is an undamped single degree of freedom. So, now if I want to take this and make it into include damping at the single degree of freedom level, how should it look? It should look like this. This is how the damped nth modal equation look like, right? This is how it should look, and note that by definition Kn is omega n squared mn. This is known. So, therefore, we should say that Cn is equal to 2 xi n omega n mn. Analogy to single degree of freedom system, because this is still the single degree of freedom. So, all that we say is that if Cn could be this. So, what does that mean? This means that it is perforce that your phi n transpose C phi, which is n by n, n by n, n by n, is also a diagonal matrix. C has to be such that you get this, and then this C n is equal to 2 xi n omega n mn. So, C matrix has to be such that these are diagonal and that C n is equal to 2 xi n omega n mn. Okay? Now the funny thing that happens is the following, okay? And that is that what happens? We have a peculiar situation that if C is of the form this, if C is equal to this, or C is equal to this, or C is equal to this plus this, since M and K are, so therefore, if I substitute this in, let us see if I substitute this, okay, what happens? Mass proportional. If suppose the stiffness the damping matrix is mass proportional, damping matrix mass proportional. What happens? Okay, if C is equal to alpha m, then phi transpose C phi becomes phi transpose alpha m phi. Alpha is a scalar, so this becomes alpha into phi n transpose m phi, and since we know this is diagonal and alpha into diagonal, this is the diagonal matrix. So, C is diagonal and therefore, we can uncouple it. Okay? So, this is what is known, that is the reason why we call it proportional damping. That C matrix, now note that similarly, if C matrix is suppose the C matrix is stiffness proportional. You can again do this, as you substitute, you will get phi transpose K phi. You know that that's uncoupled. Okay? So, therefore, and then we talked about Rayleigh damping, right? Remember last time we talked about Rayleigh damping? Well, it's obvious, I am not going to go this. Phi transpose will just become phi transpose m plus phi beta into phi transpose K phi. All of those are diagonal. So, therefore, if you have proportional damping, okay, you will be able to use you will indeed for a damped system get and now note that the C matrix is an unknown quantity. C matrix is not known. However, we can say that look, Cn is equal to 2 xi omega n Mn. So, therefore, extensively understand that as long as we make an assumption on proportional damping, okay, as long as we make an assumption of this proportional damping, this is fundamental and not derived. Okay. This is fundamental and it is not derived. What is to be derived is, given this, what is C? Now, you may well ask me that why do I need to find out C? Okay. Please understand one thing, and that is that we have a situation where if you are using mode superposition, okay, for a damped system, you don't need to find out the C matrix. Why? Because you don't you don't require to do this. The only thing that we say is that look, we don't know what C is. All we say is that the C matrix is a proportional damping such that this is a diagonal matrix such that we can uncouple the equations. Otherwise, you see, if this is not diagonal, what happens? Even if M and K are uncoupled, if the Cn are not uncoupled, then you through this Ca, the C, you get all the other y1, y2, y3, the other y's coming in, and then then the mode superposition is not a really useful, because all you are doing is taking it from coupling from one end into another end. Okay, but remember what I said, that look, we do not know what damping is. We make an assumption on damping, and we also say that look, this we don't know, it is some xi. It's not even xi n. I don't even know what xi n is. How can I find out the damping in every mode? I can't. I have no clue. All I know is that I define damping in every mode to be given by xi, and note that I don't need to know this C matrix at all. So, therefore, if you have a linear system, as long as you are linear, okay, just every mode define this. This becomes the property of every mode, and if this becomes the property of every mode, then you see, damped system, as long as damping is proportional. As long as damping is proportional, Mn Yn double dot plus 2 xi n, and note that this is again the damped single degree of freedom system we have already solved. As long as the time variation is known, okay, and you find this out, by and large the time variation is of a specific type. So, it's not even as if you have to find out for different ones in different ways. Okay. So, if you have a harmonic load, all you need to do is now instead of omega, you have omega n. So, each mode is omega bar upon omega n, and so that's you have to evaluate it for each mode. If it's periodic, well, so be it. It has omega bar n upon omega n, so it just becomes much more complicated. That's all. But complicated in computation, but not complicated in its basic analytical formulation. It's this level of this thing is almost as if going from harmonic to periodic. We had to consider omega bar as n. Here, it's like going from single degree of freedom to multi. So, it's like going from harmonic to periodic, excepting that in periodic you have infinite, here you have finite. Okay. There is nothing else in it. And the other point that is there is that I mean, if you have pulse load, if you have impulse load, if you have a general arbitrary load, you use the Duhamel integral, use the frequency domain approach for each one. Note that the complexity, I have not taken an n degree of freedom problem and made it into a single degree of freedom problem. All I have done is I have taken an n degree of freedom problem and broken it in the mode superposition method, broken it up into n single degree of freedom problems. So, the order of magnitude of the computation goes down one level, but you still have to do n single degree of freedom problems. Okay? So, that in a sense is the mode superposition method, and it is equally valid for undamped and damped as long as you have what? As long as you have your basic concept of proportional damping in place. And when is proportional damping in place? Well, typically, when you have a structure made up of one material, it's by and large okay. We can actually show later on. I am not going to show in this course, it requires an advanced dynamics course, where you can actually show that even if it is not made up of the same material, we can, in a way, it will not be a xi here, the xi becomes just xi n. Okay? Big deal. It still is, I mean, I can classically put it in this format. It still does not, make the problem more complicated. Where the problem gets more complicated is when you have what is known as non-proportional damping. Again, in this course, I am not going to tackle. I am just introducing the concept that people have considered the situation where you have non-proportional damping, and then there are ways and means of getting it, and that is the reason why in a way it is important to get the C matrix. We will see that in the next class. But in a sense what we have over here is the following, that if you look at this particular problem, the mode superposition technique essentially breaks it down into smaller problems. The other issue that comes in is, can we reduce the problem further? And this is something that we see. Because of the nature of phi n. Okay? See, as you go, I have said yesterday, as you go from this, remember yesterday phi 1, 1, 1, the lower mode, and phi 2, omega 2, the higher mode. Okay. Now, what happens is, what is Pn? What is Pn? Pn is the contribution of the load vector in nth mode. Now, if you look at a load vector P, okay, typically let's look at a kind of a situation. What I mean, let's take wind loading. Let's take wind loading, right? You have a multi-storied building. Since I am not solving the problem, I can make it as complicated as possible. Right? Okay. And what kind of load? This is being subjected. This being subject to wind load. What kind of thing that do you have? What's typically done is that you will have a basic what is this? This is the amplitude, and then you have a time variation which is there in every one of them. This is typically how loads are. The time variation is independent of this, right? So, what you have is, how would this be? This would increase, this would go something like this, wouldn't it? This would increase. So, if you look at my PT vector, it would look like 1, 2, 3, 4, 5 or something like that. I am just taking it linearly into xi of t. So, typical loads are these. If you look at these, okay, these are simple kind of loads. If you have earthquake load, it will be like inertial load, all of those kind of things. We will come to it later. But loads are typically of a form such that if you look at phi n, as n increases, what happens? The phi n is a higher energy mode. Okay. So, if higher energy mode, and PT is typically is simple. If you look at phi n transpose PT, which is Pn of t, okay, PT is given by some vector P into xi of t. So, this basically becomes phi n transpose into P naught into xi of t. So, essentially the phi n transpose P 0, which is independent of xi of t, is what we need to look at. As you get higher energy mode, okay, the mode shape vector also has more and more nodes. We will tell you what that means. And this value, which essentially is like a P0 n xi t, this P0 n, the amplitude of the load in the nth mode, this actually goes down as you increase n. So, P naught n decreases as you increase n. So, what happens is, if the higher modes are not being excited, if the higher modes are not being excited because there is no loading, and typically what do you have? Typically you have this kind of a situation. It is a 0 vector. With 0 vector, you can see that yn 0 is also equal to this, is equal to 0. So, if they are at rest, every mode is at rest because the initial velocity is at rest. If it is at rest and it is not being subjected to any load, the higher modes, the yn of t as n increases will go down, yn will go down. Okay. So, therefore, we can neglect the higher modes, and that is actually the beauty of mode superposition, because mode superposition, since you can neglect the higher modes, okay, you only consider m modes which are substantially lesser than the n. So, let us say you have a structure which has 1000 degrees of freedom. This is not unusual. Even in a framed building, okay, you can have thousands of degrees of freedom. So, you take, let us say, let us take 1000. So, you take a system which is actually 1000 coupled linear differential equations, and you make it into just 5 or 6 single degree of freedom systems, because the higher modes are not excited, and this m, the number of modes that are excited are typically of the order of 5 or 6, even if it is 1000 degrees of freedom. Now, have you reduced it? You have taken 1000 coupled equations and transformed it into 4, 5, 6 single degree of freedom system problem. That is the huge numerical efficiency that you get from mode superposition method. Okay? So, I shall continue with the dynamic response to single degree of freedom, I mean to multi degree of freedom system, to various kinds of loads. And here I will not look at specific loads like I did harmonic, periodic, because you see, if I bring it to a single degree of freedom, I do not need to explicitly get it. But what we need to do is, we need to look at some special kinds of loads and see how to get that, first how to get the equations of motion. For example, earthquake. How do I get the equations of motion for an earthquake kind of a situation for a structure? Okay. So, we are going to do that, and once I do that, okay, we will look at we still have not talked about, we only said proportional damping, it works. We will have to see how we can get proportional damping. We will look at damping in a little bit broader sense for multi degree of freedom system problems. Okay. And finally, we will look at some examples to solve, to show you that indeed m is significantly less than n. Okay. So, that in essence is what I shall be looking at, dynamic response of multi degree of freedom system problems. Thank you. Bye.